Okay, this video is going to be about the ideal gas law. What we're wanting to do is explore relationships between macroscopic properties of gases and the ideal gas law. So we're going to learn about the ideal gas law, which is an equation, Dalton's law of partial pressures, and something called the mole ratio. We're also going to learn about how to use these in stoichiometry calculations. So basically how to put some stoichiometry to this. So first of all, we just need to define some things. Volume is the amount of space a gas takes up. Pressure is the force exerted per unit of area. Now, volume, we already know, unit is usually liters. Pressure, the unit we usually use is ATM, 1 atmosphere. That stands for atmosphere. Sometimes you'll see it in torr. 1 atmosphere equals 670 torr. Sometimes we'll have to use that in a stoichiometric calculation to be able to change atmospheres to torrs and torrs back to atmospheres. Okay, temperature, definition, is the average kinetic energy of the particles in a substance. Normally we use Kelvin to measure this, where 0 degrees Celsius equals 273 Kelvin. Okay, so these three are related to each other. How much space something is going to take up, the force exerted, and the kinetic energy is how fast it's moving, affect each other. So first we're going to look at the relationship between pressure and volume. There's a law that goes with this called Boyle's law. And it's written as P1 V1 equals P2 V2, where P is pressure and V is volume. We can use this calculation if we have numbers that aren't easy to figure out, or we can just know that as the volume goes down, the pressure goes up. They are an inverse relationship. They're inversely proportional to each other. So like in this chart, if I know the volume is 1 and the pressure is 2 at the beginning with, pressure's 4 and volume is 1, and later on I want to know the pressure, and I know the volume is half, I can find out that that pressure is now 8 atmospheres by solving for x. And that's easy to do. But if it's a simple number like this, I'm not going to do that. What I look at here is that the volume was half, so I'm going to double the pressure. Here, the volume is double, so I'm going to half the pressure. 4 divided by 2 is 2. Here, the pressure got multiplied by 4, so here I'm going to divide by 4. Okay, because this relationship is inversely proportional, it works like that mathematically. And for the 0.25, well, from here to here, I divided by 4. So from here to here, I'm going to multiply by 4. Now, each of these I could have plugged into the equation to get the answer, but these were such simple numbers I didn't need to, and this is going to save you time on quizzes and tests if you know how to do this without using a calculator. Okay. right, the second relationship we have in gases is that of volume and temperature. This falls under Charles' law. Charles' law is V1, volume 1 over temperature 1 equals volume 2 over temperature 2. Which basically means that if the volume goes up, the temperature goes up. They're directly proportional. So if I double one, the other is doubled automatically. For pressure and temperature, we call this Gay-Lussac's law. Now, each of these were named after the people who discovered their realities. This is where pressure 1 over temperature 1 equals pressure 2 over temperature 2. So here, if the pressure increases, the temperature also increases. If one doubles, the other doubles. If one is halved, the other is halved. These also are directly proportional to each other. So if we use these laws and we look at something like, oh, hold on, I forgot. There's still one more law I have to talk about real quick. Okay. It's a lesser known one, so I forgot to say it. And this one is N stands for moles. If moles goes up, volume goes up, and this is called Avogadro's law. Okay. If moles goes up, the pressure also goes up. The equation for this is P1 over N1 equals P2 over N2, where N is moles. And for down here, volume 1 over N1 equals volume 2 over N2. These are also directly proportional. Now, if I'm solving for a problem like this, I can either use the equation or my knowledge. Okay, let's go ahead and use the equation for kicks. All right, so I have 1 mole and pressure of 4. So my pressure for the first one is 4, my moles is 1. I don't know what my second pressure is, but I do know what my second moles is. If I solve for x for this one, I end up getting x equals 8. And this would be in atmospheres, because that's what the pressure is here. Now, I didn't have to do it that way. I could have said these are directly proportional, so as one doubles, the other doubles. If this doubled, then this is going to double. If this multiplied times 4, I'm going to multiply this by 4. This one got divided by 4. I'm going to divide this one by 4. And that's the way I would really do it on the test, but if I forgot, I can fall back to the equation. And the same here. I can either set up the equation using this by saying volume 1 over moles 1 equals volume 2 over moles 2, and solve, get x equals 40 liters. Or I can say, hey, I know this doubled. This one's going to double. I know this one multiplied by 4. I'm going to multiply this one by 4. This one got divided by 4. Let me just go ahead and divide this one by 4. And if I can see the numbers really easily, I'm just going to do it in my head. If not, I'm going to use a calculator. And I'm going to use my equation. Either way works very fine. Now, all these relationships work together. Every time I increase the moles, the volume increases. Every time I increase the mole, the pressure increases. Every time the pressure increases, the temperature increases. Every time the volume increases, the temperature increases. So if you note, volume, temperature, and moles always go the same direction. Okay? Now, the one that doesn't go the same direction is my volume. My volume goes opposite direction. Okay? What they've done is they combined all of these items into one equation, and they formed the ideal gas law. So if I'm dealing with all of these at the same time, I don't have to jump from equation to equation to equation. I can just use all of them at the same time. And used to, in order to remember what this equation was, I would say it's pervnert. Pervnert. PV equals nRT, pervnert. Just help me remember it. Now, this R is a constant. This is going to be given to you every single time. And this constant tells me the units I have to use in this equation. If I notice, liters, so my volume has to be in liters. Atmosphere, my pressure has to be in atmosphere. Moles, of course moles is moles. Temperature, K, my temperature has to be in Kelvin. In order to get Kelvin, you add your 273 degrees to the degree Celsius. I must be in these units to be able to use this gas constant. Now, there's other versions of the gas constant that use different units, and if you're given that, you would use different units. But the one we have here is the most consistent, the one that's normally used, and this is the one that will be used on the AP test. Okay. So, let's go ahead and move on. So let's go ahead and use this in a couple of problems. So here, we've got pervnert, PV equals nRT. In this equation, it's asking me about the pressure, so that's going to be my X. My volume, 25.0 liters. My moles, 4.25 moles. My R, always given to me, 0.08206 liters times atmospheres over moles degree Kelvin. And then lastly, my temperature is given to me in Celsius. So I need to add 273 to it to get Kelvin before I can use this. By putting the right units in there, my liters, as I'm doing the math, are going to cancel out. My moles are going to cancel out. My Kelvin's going to cancel out. And I'm going to be left with atmospheres for my pressure. So when I go ahead and solve this mathematically using my algebra skills, I'm going to end up with 4.09 atmospheres as my answer, rounded to 3 sig figs. Okay, when I do the next one, PV equals nRT, pervnert. This time they gave me pressure in atmospheres. They're asking for volume. I've got 1 mole. R is 0.08206 liters atmospheres over moles degree Kelvin. And my temperature is 50 degrees Celsius, which I need to change to Kelvin by adding 273 to it. And I get 323 Kelvin. Once I do this, atmospheres are going to cancel out. Moles are going to cancel out. Kelvin's going to cancel out, leaving me with liters as my unit for my answer. So when I do my math on this one, I'm going to get 27.2 liters rounded to 3 sig figs. Okay, one last one of this. Pervnert again. Pressure in this case, they gave me 1.05 atmospheres. Volume, liters, they did not give me liters, they're asking me for it. Moles, they did not give me moles, but they gave me grams. So I need to convert grams to moles to use in my equation. So I'm going to divide by the molar mass, like I always do, to go from grams to moles. And I'm going to get 0.0078125 moles of oxygen. I do not want to round a number that's this small because it'll throw my whole answer off. So I'm going to use the whole thing. It is not a final answer, so I'm not rounding it. So 0.0078125 moles times R, which is 0.08206 liters times atmospheres over moles degree Kelvin. And then I need my temperature in Kelvin, so 25 plus 273 gives me 298 degrees Kelvin. Once I do this, atmospheres are going to cancel, moles are going to cancel, Kelvin's going to cancel, leaving with a unit of liters for my final answer. I do the math on this, and I get 0.18 liters rounded to 2 sig figs, because this here in the problem only had 2 sig figs. Okay, so that's basically how you deal with the ideal gas law and these relationships between pressure, temperature, and all that jazz. You do need to spend some time learning these relationships, especially which ones are directly proportional and inversely proportional to each other, because there's going to be a lot of different questions that are going to come up using those. Okay. All right, now we're going to move on to the law of partial pressures. Okay, this law is very easy, deceptively so. The total pressure of the gas of a container is equal to the sum of all the partial pressures of each gas. So basically, if you have gas A, gas B, gas C, so on and so forth, add them all up, that's the pressure of the total. Each individual pressure acts independently of each other, so you can add them up later. Okay? We also have the fact that the partial pressure of any particular gas A is going to equal the total times this mole fraction of gas A. What's a mole fraction? A mole fraction, which is represented by XA, equals the moles of A over the total moles. This is a mole fraction. We're going to use it in a few moments in a problem, so it'll be easier to see. Okay, so this first problem, it says the total pressure of a mixture of H2, He, and Ar is 99.3. Then it goes to tell me the partial pressures of each gas. Partial pressure of He is that. Partial pressure of argon is that. And it wants to know the partial pressure of hydrogen. So we're going to use this equation here. And I'm going to draw it out so you can see what the equation means. And then I probably won't do that ever again. Okay, so partial pressure of A, B, and C. In this case, A is hydrogen, B is helium, and C is argon. So I'm going to write like this. The P of the total is going to equal the partial pressure of H2 plus the partial pressure of He plus the partial pressure of Ar. Whoops, I almost made a bad mistake. That's not supposed to be capital. There we go. Oh, there we go, right there. Okay, that's better. So A, B, and C just represent the gases that you're using this time. So if I want to know partial pressure of one, well, the total pressure is 99.3. The pressure for hydrogen is what we don't know. That's what they're asking us for. The pressure of He is 42.7. The pressure of argon is 54.7. And in both of these are kPa. All of these are kPa. Kilopascal is what kPa stands for. It's another unit of pressure. And since all of these are given to us in kilopascal, I'm going to write my answer in kilopascal as well. So when I quickly solve for this, my answer is going to be 1.9 kilopascal. Now here's a good time to note something that we haven't ever talked about before, at least not in my chemistry class. And that is the sig-fig rules for subtraction and addition. They're different than multiplication and division. If I'm adding and subtracting like I just did, instead of going to the least sig figs, I'm going to the least decimal spot. What do I mean by that? Well, let me show you. Okay, so this number only had one decimal spot. This one only had 1 decimal spot, and this one only had 1 decimal spot. They were each rounded to the nearest 10th. So the least decimal spot is a 10th spot. So my answer here needed to be rounded to the 10th spot because I was adding and subtracting these numbers. Okay. All right, let's move on. All right, this next one. Gas mixture is 60% argon, 30% neon, 10% krypton. If the pressure of the mixture is this, what's the partial pressure of each gas? Well, that's pretty easy because they told me what percentage each one was. So argon, of that 80 kilopascal that everybody is, it is 60% of it. So I'm going to multiply by that 60%, and I'm going to find out that it is 48 kilopascal. Neon, of that 80 kPa, kilopascal, that the whole thing is, 30% of it is neon. So I'm going to multiply by 30%, and I'm going to find it's 24 kilopascal. And krypton, the same deal. Of that 80 kilopascal that existed, 10% of it was krypton for a total of 8 kilopascal. Okay. Now, if I want to double check myself, these all should add up to be 80, and they do. Because the partial pressure of each one should add up to be the total. All right, moving on. Now this one. Cylinder contains that many grams, and that many grams. What's the moles of each gas? Well, that's pretty easy. 40.0 grams of helium. Quick stoichiometry, 4.0 grams of helium in 1 mole of helium. And I get 10 moles of helium. This has 2 sig figs, this has 2 sig figs, that has 2 sig figs. I'm going to round to 2 sig figs. Okay. Now 56.0 grams of N2. Molar mass of N2 is 28.02 grams of N2 in 1 mole of N2. So this one will be 2.0 moles of N2. Last but not least, I have 40 grams of argon. Argon's molar mass is 39.93 grams for 1 mole. And that equals 1.0 moles of argon. Okay? Now, it asks us, well, what's the total pressure of the mixture? I'm sorry, the total pressure of the mixture is 10 AM. What's the partial pressure of helium? All right, that's where we're going to have to use this up here that we went over just a few moments ago. The pressure of a particular gas. So in this case, the pressure of helium. Equals the pressure of the total times the mole fraction of helium. This equals the pressure total times this mole fraction of helium. Okay. So make sure that's a dot here. This is multiplication here. Okay, there we go. Now, we also saw that this mole fraction, Ka, is represented by moles of A over total moles of A. So let me rewrite this real quick. The pressure total times moles of He times the total moles. This is the symbol for the mole fraction. This is how you calculate the mole fraction. So you see here, the A in this case was a gas. This time the gas is He. So the moles of He over the total moles. Now that I've got that written down, this is pretty easy because we want to know the pressure of helium. That equals the total pressure, which they told us is 10 atm, times the moles of helium. Let's see, the moles of helium was up here. We just calculated that 10 point. Why do I write the dot after? Remember, that's going to make that last zero significant. Okay, all right, so 10 dot moles of helium over the total moles. Well, there was 10 plus 2, 12, plus another one, 13 moles in the whole entire mixture. So the partial pressure of helium ends up being 7.7 atm. Okay, some things to note, very, very important information. You're going to be using this in your practice problems. If it says STP, that stands for standard temperature and pressure. Standard temperature is always 273 Kelvin, and standard pressure is always 1 atm. When it is at STP, when it's at the standard temperature and pressure, under those conditions only, the volume of 1 mole of gas is 22.4 liters. So 1 mole of gas will be 22.4 liters at STP. So if it says STP, it's telling you more than what it's giving you in the problem. It's telling you that 1 mole of gas is 22.4 liters as well. But only use that if the gas is at STP. If not, that doesn't apply. Okay? So go ahead and you do the practice problems. Ask me if you have any questions. Be careful down here because, which one was it here? Oh, I forgot. I'm going to have to show you that too real quick. Millimeters of mercury. Okay, let me add that to right here. I'm going to go up a little bit to where I had that other conversion. And I'm going to write that down the same spot, which was right here. Okay, so on the very first page of these notes, I said 1 atm equals 760 torr. Okay. I'm also going to write down that 1 atm equals 760 millimeters of mercury. mmHg stands for millimeters of mercury. Okay. Obviously, with these two equations, you can see that torrs equal millimeters of mercury. Okay, because 1 atm is 760 torr and 1 atmosphere is 760 millimeters of mercury. So, if you have millimeters of mercury or torr, you have to get to atm first. Use these to help you convert. Right? And that should be it.